Great day! Information is pretty great. It is actually my top 4 favorite thing. It might not sound impressive until you realize that the other 3 are time, life and space. So yeah, I would say information is quite up there. We as humans are kind of programmed to like information, and its only downside actually is just being repetitive. So let's start going over why information is so great with hidden information and the good old Monty Hall problem. First, let's review the thing.
So let's imagine a game show with a host and 3 boxes. Now inside one of the boxes is a secret to happy life. Or maybe just an apple, because that's easier to animate. Now you will be able to pick one of these 3 boxes. So you look away and the host mixes them up. Now when you look back, every single box has a 1/3 possibility of having the apple in it. That's pretty obvious. So then you choose one of the boxes and the host, who knows where the apple is, shows you the box which does not have an apple in it and is not yours. Now the question is, should you switch? I mean, it doesn't really matter. Every single box has a probability of 1/2 of containing the apple, right? Right?
Yes, that's the beginning, and now we're coming to the part when I'm telling you that half and half are not the true probabilities, and in fact it is 1/3 and 2/3, which is very surprising, and then I go on to explain why that is the case. But there is a question that's more important than why is it 1/3 and 2/3. The question of why is that surprising to us? If you think about this logically, it makes sense. It really makes sense that it is 1/3 and 2/3. So why is it surprising on the beginning? Well, it's because our brain is missing some information. Our brain thinks that setup looks like this. Once again, we have 3 boxes and the host chooses a random box. Opens this box, there is nothing inside. What is the probability of each box containing the apple? Those 2 are not the same. In our case, we actually have more information than that. We know that the host would never pick our box, and we know that the host would never pick the box with an apple in it. That information is important, and based on that information we can see that probability of the box we didn't choose is actually 2/3. The part that the host chooses the box that is not ours is what actually is tilting the probability so severely. Because the host cannot choose our box, it makes sense that our box would have a different probability than the other one. Because in 1/3 the cases, the host would actually have 2 reasons for not picking our box. In the other 2/3, they would have only 1. And so that's the... Oh, come on, man. I'm recording a video here. It's not time for meta stuff. Sorry about that. What video are you watching? Information video, rather important, if you don't mind. Alright, well, I kind of need to get the thing that the thing that's too early for meta stuff. My goodness, it was 3 minutes into the video. Alright, let's move on to the next thing, doesn't matter. So, hidden information can be problematic because we often, when we are trying to find some answers to some questions, we just seem to stumble onto the wrong path because we can't find the correct information. But it can be also problematic because the information can repeat, the redundant information. And the best example of that would be chess notation.
Chess notation is really often used because it is more convenient to just read a small note than to recreate an entire chess game on a chessboard. But it has a problem, because you see, chess notation sucks. Now, in order to understand why that is, we have to take a closer look at the notation itself, and in order to see how we can optimize it, we have to talk about the smallest and most efficient unit of information: a bit. Many people think that bit is just a number, a 1 or a 0, but in fact it is just an answer to a question. The simplest answer there is, yes or no. It is really often used in computer science because it is the base for all the logic inside a computer. In this shot we can see, after zooming in through the incompetence of the cameraman, that the light is lit when the battery is connected. In this case we can say that a bit could describe if the battery is connected, 1 if it is, 0 if it isn't. But bits don't have to represent electricity. They can represent a light bulb being lit, a faucet being on, or can help us describe a more efficient chess notation. By describing it with a binary number, we can say that the first digit represents the color of the pieces, the second digit could describe if it's a pawn or a piece, and then the next 3 digits could tell us which one is it: first, second, third, fourth, fifth, sixth, seventh, or eighth. So now we can describe any piece on the board with a binary number. The only thing left to do is describe where is this piece going to go, and in order to do that we have to check what's the maximum number of moves a piece can have. And in order to do it we just have to put a queen in the middle of the board, and see that it has 27 moves. So the maximum is 27. So we can describe movement of any piece using only 5 binary digits, which means that we can describe any move with only 10 bits. Except we do not need all of them. This was a test and you failed. Unless you didn't, then good job. Because we can only use 9 bits, we don't need to know which color moved because that can be calculated based on how many moves there were. Every even move is black and every odd move is white. Now in our original notation we have 24 characters, which meant that we needed 5 bits to describe a single character. Now the shortest possible move takes 3 characters, space included as a termination character, and the longest takes 9, which would give us the average of 30. Now even though this average is incorrect because longer moves are more rare whilst the shortest moves are more common, it still gives us 45 bits for the longest move and 15 for the shortest, which is worse than our 9 every single time.
And so there we go. But here's the thing, I am not actually that smart when it comes to coming up with the chess notation, and it's kind of obvious for any programmer out there who programmed in C or C++ that would be the better way to do it. So why is chess notation what it is? Well, so why are we using the suboptimal chess notation? Well, in order to understand that, we'll have to understand what kind of prior information is required in order to read the information.
So when it comes to our chess notation, first thing you have to do is go through the entire game and decode every single bit of information in order to get the correct board. Then you have to wind this snake pattern throughout the entire board to actually check which move will be the first or the second or the third for any given piece. Oh yeah, I guess I forgot to mention about that. Basically you have to wind this pattern throughout the entire board because whilst that is true that there is a maximum amount of moves that a piece can have, we don't really have the best system for calculating where should we start counting those moves, so just any arbitrary snake pattern would work. Then you have to check your available moves, and only then you can read the actual bits. And that is actually a lot of work if you compare it to the no chess notation, where you can just read 2 characters, and there we go. You know that the A pawn will move to the 3rd square.
And so because of that, even though chess notation is not the best when it comes to storing the highest amount of data on a computer, it doesn't have to be. That's not what it was made for. It was made for just, saving the chess games one with some pen and paper, and it works just fine. It is easier to read for normal humans. That's why it stayed around. It stayed around. That's a neat segue, let's use that. Alright, so there isn't much to say about this topic, so I'll just keep it simple, some simple animation with editing make it we're talking. So yeah, editing make it, take it away.
We'll do some make it because first law of thermodynamics tells us that energy cannot be created or destroyed, and it just so happens that energy is information. And because of that, if you took the sample of the entire universe, stopped it in time and counted all of the energy, it would be always the same. Just like if you stopped the entire universe and extracted all of the information, it would also be always the same. There would be the same amount of information. This is obvious. That's why this segment is so short. Instead, let's go for the interesting thing, which is information loss.
And so yeah, information cannot really that much be lost. Anyway, now on to the probably last bit, so let's go.
Now, even though information loss does not happen in nature, it really often happens in our information medias. For example, images. Let's imagine some random image. We could describe this image as an image of a bike, a forest, or a cloudy sky. Based on all of those descriptions, we could generate some more images. Now, all of those images would carry the same amount of information as the original one, but everything that we did not specify in our description would get replaced by some random information. For example, bikes would no longer be in the forest, the sky would be clear, or there would be no wheels around. That's information loss. Even though our medium is not losing our information, we might not copy all of it. That's why if you take an image, describe it with words, and use it to create a different image, you wouldn't get the original image. And that's why if you take the screenshot of the universe with data about all of the particles, all of the energy, and all of the ways saved, then you could predict how the universe looked like in any year, past or the future. It's because the amount of energy which stores the information of the universe and the amount of information it carries is constant.
Now it's really interesting though. Just like images, videos are also imperfect. They cannot carry all the information. And because of that, there are many things in this video which are rather ambiguous. You are not actually certain why I'm doing some of these things. And I myself find that rather beautiful. Not because you don't know, but because you're curious nonetheless. You still would like to find out more. And that is rather beautiful. The fact that even though you don't know, even though you don't know if you want to know, you still will try to find out. So, and that's why I think that information is pretty great. So, thank you so much for watching, and have a great day. Information is pretty great. It is actually my top 4 favorite thing. It might not sound impressive until you realize that the other 3 are time, life, and space. So yeah, I would say information is quite up there. We as humans are kind of programmed to like information, and its only downside actually is just being repetitive.